Welcome to this explainer. We're jumping right in today because we have a genuinely fascinating mathematical plot twist to uncover in the world of quantum computing. We hear all the time about how quantum computers are going to revolutionize, well, pretty much everything, right? But how do we actually measure that advantage fairly? Today, we're exploring a really groundbreaking paper by Itzhak. It introduces a new algorithm called Q-weight. But honestly, more than just giving us a cool new algorithm, this research exposes a hidden cheat sheet that classical algorithms have been using in benchmark tests for a long time. So let's dive into this and see how we are finally leveling the playing field. But first, let's ground this. Have you ever just stared at a loading screen, waiting a little too long for a server to respond? Or maybe you've been put on hold endlessly by a call center, listening to that same loop of elevator music. It's a universally frustrating experience. But behind that simple annoyance is a massive, incredibly complex queuing system. Modern digital infrastructure, like global cloud computing networks, relies on these exact kinds of queues to handle millions of requests every second. And when the digital line gets too long, things break.
Which brings us directly to the SLA, or Service Level Agreement. You can think of the SLA as the ultimate line in the sand. It's a strict threshold defining the maximum acceptable wait time before a system officially fails its customer. For the engineers running these networks, predicting exactly how often a complex, highly unpredictable system is going to breach this SLA is a notoriously difficult mathematical challenge. It's basically trying to predict a very rare event in a highly chaotic environment.
So here's our roadmap for today's explainer. First, the problem with queues. Second, we'll enter the world of quantum amplitude estimation. Third, we'll see exactly how Q-weight works. Fourth, we'll look at that fair baseline benchmark I mentioned. Fifth, testing Q-weight's actual performance. And finally, circuit costs and feasibility.
Part 1. The problem with queues.
See, for simple, predictable queues, we have neat little mathematical formulas. But for real-world scenarios, like heavy-tailed cloud workloads where a few massive tasks can suddenly just clog up the whole system, there's no closed-form math for that. None. Engineers have to rely on classical Monte Carlo simulation instead. They essentially simulate the queue millions of times to guess the probability of an SLA breach. But here's the core conflict. To get a precise estimate, classical systems require a massive squared number of samples. If you want high precision, the computational cost skyrockets exponentially. Quantum amplitude estimation, on the other hand, promises a provable quadratic speedup. That means it requires vastly fewer computational steps to reach the exact same precision.
Which leads us to Part 2. Enter quantum amplitude estimation.
This is where Weinberg introduces Q-weight, which stands for Quantum Accelerated Waiting Time Tail Estimation. Now, this algorithm doesn't try to simulate the entire dynamic movement of the queue on a quantum computer. That would be way too messy. Instead, it just takes the stationary distribution, essentially the long-term stable state of the queue, and leverages something called Iterative Quantum Amplitude Estimation, or IQAE. By doing this, it accurately predicts when wait times will exceed our acceptable SLA thresholds. It's highly targeted and it's incredibly efficient.
Part 3. How Q-weight works.
The mechanics of Q-weight actually break down into three pretty smooth phases. First up is state preparation. This is where the algorithm takes the queue lengths or wait times, discretizes them into bins, and loads them into a quantum register using amplitude encoding. Second, we have the comparator oracle. Think of this as a brilliant little alarm circuit. It flags a dedicated target qubit, an objective qubit, if the queue length crosses our SLA threshold. It literally screams, "Breach!" Finally, estimation. The algorithm runs that iterative quantum amplitude estimation on this setup to estimate the exact probability of that tail event occurring, narrowing down the confidence interval with every iteration.
Section 4. A fair baseline benchmark.
Okay, here's that methodological plot twist we talked about. For a long time, classical algorithms have secretly been given a massive head start in these benchmark tests. The standard comparison uses what's called a central limit theorem, or CLT, baseline. But here's the catch. The math for the CLT baseline actually uses the target probability to calculate how many samples it needs. It assumes the answer in advance. The quantum algorithm doesn't get to peek at the answer like that. So, the author strongly argues we have to use a fair classical baseline, specifically the Chernoff-Helfing bound. This bound is distribution-free, meaning it doesn't cheat by looking at the probability beforehand. It holds the classical algorithm to the exact same rigorous standard as the quantum algorithm's own confidence interval.
Moving to Section 5. Testing Q-weight's performance.
This comparison brilliantly illustrates the difference. If you look at the query complexity versus the actually achieved precision, you'll see a clear split.
The fair classical baseline scales perfectly at an exponent of -2.00, exactly as theory predicts. But then look at Q-weight. When you actually compare them fairly, Q-weight's empirical speedup rapidly grows from a 7 times advantage to a massive 30 times advantage as the target precision gets tighter. Against the old unfair baseline, classicals sometimes look better, sure, but when held to the same statistical rigor, the quantum advantage is absolutely undeniable and it just keeps growing.
So, the real test is what happens when we throw a really messy real-world problem at it, right? The researcher tested Q8 on a non-Markovian queue. That just means the system has a memory of past events, which creates highly unpredictable, heavy-tailed service times. It's exactly the kind of chaotic workload you see in major cloud computing centers where there is no simple math to save you. And the results? To achieve a matched precision, Q8 required a 42.1 times reduction in queries compared to the fair classical baseline. Literally 42 times less sampling work to find the same rare SLA breach. That is a game changer.
Finally, Section 6. Circuit costs and feasibility. We have to address the elephant in the room here. Does this theoretical speedup require quantum hardware that is just totally impossible to build? Well, notice how perfectly straight the lines are for circuit depth, gate count, and ancilla, meaning extra help or qubits, as we increase the resolution of our Q discretization. The fact that these scale in straight lines proves that increasing the resolution only requires linear hardware overhead. We completely avoid an exponential blowup in the Oracle circuit, which is incredibly good news for actually building this in the real world.
But we do need to transparently acknowledge a limitation. While that comparator oracle scales linearly, the very first step, loading an arbitrary, unknown probability distribution into the quantum state, scales exponentially. It requires O of 2 to the n gates. So to scale this up massively in the future, engineers won't be able to rely on a general-purpose loader. They'll need to develop highly specific, distribution-specific loading schemes.
And that brings us to the stark reality of the near-term quantum era, which is captured perfectly by the author. They note that beyond some resolution, decoherence, not query complexity, becomes the binding constraint. The true challenge going forward, and this is key, won't be the algorithmic math. Q8 just proved the math works efficiently. The real battle will be against the quantum hardware's physical ability to maintain these delicate quantum states without error, otherwise known as decoherence.
So as we wrap up this explainer, I want to leave you with a thought to chew on. Now that we finally know how to measure the fight fairly, we can see a genuine, massive quantum advantage in predicting system failures. So as quantum hardware eventually matures and overcomes that decoherence hurdle, how will these rigorous quantum solutions completely reshape the limits, the reliability, and the sheer scale of the global cloud computing infrastructure we rely on every single day? It's a thrilling frontier to watch. Thank you so much for joining me to explore the incredible mechanics of Q8. Keep learning, keep questioning, and I'll catch you next time.